This is me and Drew's project. It's called NeuroAssist. So current day prosthetic control methods lack real-time adaptability and intuitive responsiveness. These limitations are critical for assistive technologies and for individuals with diverse cognitive states.
So the NeuroAssist framework leverages reinforcement learning with deep Q networks for motor image classification. So essentially, it looks at brain signals and classifies what muscles and what movements they kind of relate to. So it enhances the adaptability and responsiveness of brain-computer interface systems, so prosthetics driven by computers, and provides more intuitive and real-time control methods for prosthetic devices and other assistive technologies. So right now there's a lot of limitations of current prosthetic methods, but these can be minimized by integrating advanced AI techniques that kind of learn the relationship between electrical signals in the brain and movements in the body.
So why is this important? The limitations of current prosthetic control can reduce overall quality of life for users, and they may find it challenging to perform basic tasks independently. Users may remain more dependent on caregivers or assistive services, and it affects their autonomy and self-confidence. The difficulty in mastering and using non-intuitive control systems can lead to frustration, discomfort, and even abandonment of the prosthetic device.
So EEG signals are a non-invasive method to record electrical activity in the brain. So they're used by capturing neurons through sensors placed on the scalp. So as I said before, motor imagery is the mental stimulation of movement without actual muscle activation, and it activates brain regions involved in real movement, useful in these prosthetics driven by computers. So there's a lot of existing research on using neural networks for classifying these electrical signals in the brain. And there's been a lot of also trends in machine learning and deep learning algorithms for motor imagery. And as you can see, these two models right here have achieved accuracy of over 90%.
So our methodology and framework include a data science data set. So 25 subjects were recording multiple sessions of upper extremity movement tasks and 60 EEG channel setups sampled at 2500 hertz with a 7-channel EMG and 4-channel EOG signals. And our feature extraction, so the EEG channels selected were C5, C3, C1, CZ, C2, C4, and C6. And we also use bandpass filtering and power spectral density using Welch's equation. The framework was a common spatial pattern for multi-class ML classification and integration of DQN with 1D, CNN, STM for real-time decision making.
So this is one of the other data sets we used, not the one that we trained on, but one of the data sets we used to test the model. So in this one, there were 9 subjects and 4 motor imagery tasks measured. And this one was a 22-channel EEG data set. And again, it used common spatial pattern for discerning the different motor imagery classes.
So accuracy, the Giga Science data set achieved up to 100% accuracy in the ML task. And the BCI data set was high accuracy in classifying ML EEG signals. The results were NeuroAssist outperforms traditional methods by integrating DQN with our architecture.
So some applications of the program are assisting recovery of motor functions, of course, prosthetic control. So using the computers to classify what movement the user is trying to achieve. And then and then an improved understanding of brain functions related to movements. So the implications of this are better real-time adaptability and responsiveness in these prosthetics and potential for more personalized and more assistive technologies.
So NeuroAssist offers a novel approach to BCI systems with high accuracy and adaptability. It combines RL with advanced neural decoding techniques for improved motor imagery classification. And what me and Dhruv are thinking about are further testing on diverse data sets. So just using it on more and more people. And then also more applications of the product in cognitive and motor rehab.
Thank you. Does anybody have any questions?
Are you planning to submit this paper to some peer review?
Yeah, so we already have been working with a couple investors and colleges overseas and we've already published a paper. So yeah.
Where did you?
At some college in like India. Yeah.
Any other questions?
So this is essentially reinforcement learning, right? In other words, you guys have, so you guys are using neural nets to approximate the value function in reinforcement learning, or what in your overall architecture? So you have some reinforcement learning plus you're trying to maximize the value using neural net approximation. Is that the approach, or?
Yeah, so basically we want to make it as personable as possible because a regular prosthetic isn't built for everyone. So we are trying to make it as personable for the person because everyone's injuries or concerns are different. You can't just use one product and use it for everything. You have to make it as personal as possible for the user experience to be good.
Wonderful project too. Everyone selects such interesting projects and worthwhile. So the measure, the 100%, for example, so you're using AI to read the EEG and then you're predicting what movement the person made?
Exactly, yeah.
Exactly, yeah.
So, because every signal in the brain is corresponding to a movement, and so the data set is essentially describing, like it measures the electrical signal in the brain, and then visually what limb that they're moving or what movement that they're making. So when we,
Well, I think the Neuralink is what Neuralink is doing. Elon Musk company is it's actually instead of working with the prosthetics, they're actually letting the computer do the movements the person wants from his brain. So that's kind of a same learning, I think, but a different way of implementing the inference, right? So.
And then with this working, then how would you then apply it to improve someone's rehabilitation or how they're doing?
yeah. So with the model, essentially you have the device that can measure the EEGs, and so they have the prosthetic that has a computer linked to it. So essentially they try to make a movement, and then you'd feed it. The prosthetic would have the output of the model, which would be this signal in the brain. It corresponds to this movement, and the prosthetic is that movement essentially. So that using the output of the EEG signal.
That's neat. Thank you.